Hello everyone. Today our group will present our case study project on failure of a 5-story car park. I am Hirishan and I will involve in the part of the background and objective. The case study involves a 5-story car park construction using a long space post-tensioning bin system. Post-tensioning was selected because it allowed longer space with fewer columns, creating larger and more efficient parking space. However, during the construction, the full press strengthening force was applied only 3 days after casting. Shortly after strengthening, between 5 and 6 days, extensive cracking was observed throughout the structure. This crack were found not only in the beams, but also in the supporting columns, with crack width exceeding 0.7 mm, which is well above the acceptable survivability limit. Based on this case, our study has 4 main objectives. First, we aim to investigate the root cause of the structural cracking by examining both the construction process and the structural behavior. Second, we assess the material property and structural performance throughout engineering evaluation and suitable testing method. Third, we compare the structural response under 2 loading conditions: gravity loading only and gravity loading combined with post-tensioning. This comparison helps us understand how press strengthening influence the internal force within the structure. Finally, based on our findings, we propose appropriate strengthening and remedial measures to restore the structural integrity of the car park and recommend preventive measures to avoid similar failure in future projects. Next, I will pass to the next person to continue the presentation.
Hello everyone, my name is Tian Hao. Today I'm going to continue the assessment phase of our case study on the structural failure of the 5-story car park. To understand why this structural experience such as massive cracking, we have conducted a comprehensive material and structural assessment. First, let's look at the concrete property. We have carried out 3 visual tests. The first one is the compressive strength test, which helped to verify if the concrete had actually achieved the required transfer strength before the post-tensioning force was applied. The next one is the modulus of elasticity test, which help us to evaluate the concrete stiffness and understand direct effect on the beam softening. Finally, a crit and shrinkage assessment was critical to determine how time-dependent deformation influenced the restraint-induced stress between the frame. Second, we closely evaluate the reinforcement and post-tensioning system. This involved an anchorage inspection to check for any critical cracking, concrete sparing, or localized failure around the anchor. We also conduct a lift-off test to precisely verify the remaining effective pre-stressing tendon force. Furthermore, a corrosion inspection was performed to ensure the overall integrity and condition of both the rebar and tendon. Lastly, we have implemented non-destructive testing or NTD to safely analyze the inner condition of the structural element. We use the rebound hammer test to quickly assess the concrete surface hardness across different locations. These were combined with ultrasonic pulse velocity (UPV) testing, which allowed us to map out and detect any deep internal defects such as void or hidden crack inside the concrete. That's all from my part. Now my team will explain the remaining NTD method and the structural modeling result. Thank you.
Other than rebound hammer and ultrasonic pulse velocity tests, additional non-destructive tests such as crack survey and monitoring, as well as ground penetrating radar (GPR), can also be carried out. First, crack survey and monitoring will carry out to identify the location of cracks, measure their width, and observe whether the crack continue to propagate over time. This helps in understanding the severity and pattern of structural distress. In addition, ground penetrating radar or GPR was used to scan inside the concrete to verify the terrain profile and reinforcement layout. This is important to check whether the tendons and steel bar were placed according to the design and to detect any possible construction issue that may have contributed to the crackings. Next, this slide describes the structures and the representative frames selected for a structural analysis. The case study is a 5-story reinforced concrete car park with an armrest RC frame systems, a beam span of 50.6 meters, column height of 2.7 meters, beam size of 2000 times 575 millimeters, column size of 600 times 600 millimeters, and a 150 millimeters hollow core slabs. To study the structural behavior, two loading cases were analyzed. Case 1 consider gravity loads only, including the dead load, superimposed dead load, and live loads, in order to establish the baseline structural response. Case 2 include both gravity load and post-tensioning effects, where pre-stressing force, equivalent outward tendon load, and axial pre-stressing force were applied to evaluate the influence of post-tensioning on the frame behavior.
I'm Liu Jiahao. I want to talking about the case S1 gravity load only. Under this condition, our the ultimate design load reached 113 kN per meter. This is factorized from four load components: the beam cell height, the slab load, and the superimposed dead load, which is fiducial. As you can see from the internal force diagram, the heavy downward gravity load subject our beam. Especially, we observe the shear force at the support is 887 kN, and at the mid-span bending moment reach 2000 kN. Next is the case 2, the gravity load plus post-tensioning. A 50 mm diameter, 7-wire low radiation strand confirming was selected. By applying a massive press stranding force of 3000 kN, we successfully introduced an upward load of 27.18 kN. This successfully dropped our effective net beam load from the initial to the 76.05 kN per meter. If you look closely at the new diagram, the internal force distribution changed significantly to the 591 kN. So last for me is the discussion and the comparative. The net design load on the beam is cut down by using post-tensioning. The maximum shear force and moment are reduced by 22% and 21%, greatly optimizing our fractional and shear performance. From the engineering properties, introduced that 3000 axial compressive force does not cause immediately elastic beam shortening, which will further involve over time due to concrete creep and shrinkage. Because our rigid beam column connected restrain the shortening, carefully reinforcement detailing is essential. Ultimately, post-tensioning allows us to safety and efficiency maintain a slim long beam profile under an extreme load.
I'm Tawiki. Now I will explain the strengthening and remedial measure of our project. First, for immediate repair, stable crack can be repaired using explosive injection. This method restores the continuity of the concrete, prevent moisture from entering the crack, and help improve the structural stiffness. Next, a post-tensioning system inspection should be carried out. Lift-off testing is used to verify that the tendons still have the required stressing force. At the same time, the anchorage joint should be inspected for any sign of cracking, concrete spalling, or tendon damage. For structural strengthening, one effective solution is the application of carbon fiber in reinforced polymer, or we call as CFRP. This can increase the beam fractural capacity and improve crack control while adding very little extra weight to the structure. Another strengthening option is external post-tensioning. This method can help to reduce the tensile stress in the beam and improve both its long-term serviceability and overall structural performance. Finally, for the long-term prevention, continuous crack monitoring and regular inspection should be implemented. Post-tensioning should only be carried out after the concrete has reached the required transfer strength. During design, engineers should also consider creep, shrinkage, beam shortening, and restress effect. In addition, proper reinforcement, detailing, and strict quality control during tracing operations are essential to prevent similar problems in the future. In conclusion, this investigation confirmed that gravity loading alone was not responsible for the observed cracking. Although post-tensioning successfully reduced bending moment and shear force, it also introduced significant axial compression and beam shortening. When stressing was carried out at an early age, the combined effect of creep, shrinkage, and restraint from the surrounding frame generates secondary tensile strength. This tensile strength assists the tensile strength of the young concrete, leading to the development of crack. Therefore, future projects should be ensure that concrete has achieved sufficient strength before pre-stressing begins. Designers should also consider time-dependent effects such as creep and shrinkage during both the design and construction stage to minimize the risk of similar cracking. Thank you. That's all for my presentation.